We left off right around here. There'll be one of these combustion ones on the test. So we already did this one, but I just want to point out sort of the pitfalls with this is make sure, if it doesn't give you the formula, if it says oxygen gas is O2, not just oxygen, the atom. Then whenever you're doing these carbon hydrogen compounds, it doesn't matter whether you pick carbon or hydrogen first, but you need to do them before you do oxygen. And the general scheme with this, and if you like puzzles and things, this is just a chemistry puzzle. But when you're balancing an element on both sides of the equation. Always the easiest elements to do are the ones where they're only in one chemical on either side of the reaction. So, right, carbon is only in the C4H10 and in the CO2, and hydrogen's only in the C4H10 and the H2O. Right, oxygen is in 3 of the 4 species. So it doesn't matter again whether you do carbon or hydrogen first, but you don't want to try oxygen and then go back and do carbon and hydrogen, because then you'll have to redo it anyway. All right, let me go full screen. So there'll be one of those, and at the end of this section, there's a couple that are a bit more challenging than those. And then there'll be one of these easier ones. So, this is sort of putting together everything that we've talked about and seen in this chapter. Here's sort of the, the short sense. A white aluminum metal reacts with air to produce a white powdery compound known as aluminum oxide. So that's your, paragraph or whatever sentences that you learned how to pull math equations out of, years ago. And this is how we represent that in the chemical world, right? Al in the solid state, that's aluminum metal, reacts with oxygen, that's a gas, and gives a product of aluminum oxide. And then this comes from the positions on the periodic table, right? Aluminum is in group 3, so +3, oxygen's in group 6, so -2. So a 6 plus and a 6 minus charge cancels them, but now these aren't balanced. So you can see with this equation, this one's going to be easier, right? Because you only have 3 species. And the first 2 reactants only have the single element in them. They're not combined with something else. Obviously, the aluminum, this one doesn't solve it step by step, but obviously the aluminum doesn't match, right? So there's an Al2. So first you would put a 2 next to the aluminum over here. Then you go to oxygen and you can see that 3 and 2 don't match. So where do 3 and 2 meet up? Their common denominator is 6, right? So that means we need to put this 2 coefficient in front of the product. And then that changed our aluminum 2 times 2 to 4. So we needed to come back over here and put a 4 in front of the aluminum. So you can see here, they'll be on the test, they'll be in what I consider an easy one like this, and then a harder one like the combustion ones. All right, another example. Sorry, I'm just moving one of the boxes that has some of the text covered up. Acetic acid, which isn't one of the ones that I make you memorize. And it's really an organic chemistry thing. Reacts with metal aluminum to make aqueous aluminum acetate and gaseous hydrogen. All right, acids, we talked about this a little bit at the end of class. I don't know if it was yesterday or last week, but acids can come as a gas, only a few of them, hydrochloric and hydrofluoric, but for the most part, they're always in an aqueous, a water solution. Right, and then metals are solid with the exception of mercury, but I already mentioned I'm not big on testing you on the exceptions to things. So this one's saying aluminum metal and then our acid combined, and we get aluminum acetate. Right, this is one of the polyatomic ions, the acetate. It's a -1. We've got 3 of them, so the aluminum must be a +3. And then it gives off hydrogen gas. This is a real common Chem 161 experiment that is done with a variety of metals. Usually not aluminum because it's kind of slow, but it can work. Okay, so is this balanced? Well, over here we've got 3, right? So we need 3 of these acetates. I would take a 3 and put it over here in front of this acetate. That gets you started. The hydrogen that's moving is on the acetate, and if there's a 3 in front, then that has to, once again, lowest common denominator between 3 and 2 is 6. So we're going to need to change the 3 in front here to 6 because there's only 1 hydrogen, and then a 3 in front of the hydrogen gas. So that makes 6 hydrogens that are coming and going. I know there's other hydrogens in here, but they're within the polyatomic ion. They're not moving. They're not going anywhere. It's one formula unit. All right, and then if we have a 6 in front of the acetic acid, then we need 2 of the aluminum acetates, right? Because the 3 here times a number has to equal 6 acetates, and that number is 2. Then the 2 gives there in front of the product gives us 2 aluminums. We need to go back and put 2 in front of the aluminum solid. So here's another sort of test or hint. You know, the polyatomics are one whole unit. You can consider them like just one large element like X. I'd leave single elements like this to do last, because all you have to do is just, when you think you're done, when it looks like you're done, you count up that one element on the other side and put that coefficient in front of it, right? All right, the rest of this section, and we'll see more of the balancing. In my opinion, these chapters 3 and 4 are like really one big chapter. It gets too long and they decided to cut it in half somewhere. And most books do this. The rest of this is really like the first week of organic chemistry, or the second week. And it's not an organic chemistry class. So the more of this you know, the easier it'll be as you read and we do problems and stuff, but the intention isn't to test you on it. And this is sort of the, common nowadays, like food discussion about, being healthy and whatnot, or the term organic means sort of natural or healthy these days. But really this all started from back hundreds of years ago, where sort of organic was things that were compounds from the earth and were alive, and then things that weren't alive, like table salt, were called inorganic. So organic compounds you could do things with. And before the 18th century, we didn't have laboratories where you could make these things, this is the onset of the pharmaceutical world. And then inorganic compounds, very difficult to decompose, but you could synthesize. All right, so that's sort of the generic terms and has translated into the food culture of today. But nowadays, organic compounds, if you think of them from the chemistry side of it, are anything that's made with a non-metal and is based in carbon, but has a few of these other elements. And these are bioactive things, different drugs and amino acids and proteins and enzymes and all these things. But the backbone of all this, and petroleum-based things, rubbers, plastics, etc., the basis for all this stuff is carbon. And we saw this a little bit in the introduction of the periodic table, where we were putting the charges to things and we ignored carbon. And that's because carbon has 4 electrons. So it wasn't beneficial. It's right in the middle. It doesn't want to give up 4 electrons or gain 4 electrons. in the inorganic ionic sense of things. So carbon does this unique bonding because it's right in the middle. And it basically does exclusively covalent, which means no ionic. It doesn't lose the electrons, it shares them and bonds with other nonmetals. Now, since it has those 4 electrons, that means it wants 4 more electrons in a covalent. Covalent means they share the electrons. And so you get lots of options with carbon that you don't get with any other nonmetal. And if you move on the periodic table down from carbon, you move to silicon, which is one of those metalloids. So the behavior of in the group is changing as you move down. But what we care about, what you'll see in the future, and again, this is like the refresher first day of OChem, you're going to form 4 single bonds, and 4 bonds total. So then you can make 2 double bonds, or 1 triple and a single, 1 double and 2 singles, and so on. And then what is rubber, plastics, etc.? Well, that's this. It's not really limitless, but usually in a piece of rubber, they're like at most 50 or 100,000 carbons attached in a row. And then just like a tree, right? Some trees have a lot of branches and other trees don't. They are like if you've ever seen a redwood tree, right? It's straight and extremely tall versus like the banyans that we have here. That's kind of the way these carbon compounds can be. None of this will be on the test, right? There's our acetic acid. That's what we used in that last problem. This is acetylene that people cook with, or blowtorches, ethine and ethene. You can make plastics with, but beyond the scope of our class, most of you will see it in OChem. We'll come back to a few tidbits of these towards the end of the semester. Propane's what you cook with. I don't have too much to say about isobutane as far as like usefulness to the average person. And cyclohexane, it's just showing the honeycomb 6-membered ring framework. All right, so I'm not going to test you on, this thing. These things are called hydrocarbons because they're almost, 90 to 99% based on hydrogen and carbon, so they get called hydrocarbons. Inorganic is those ionic things, metals back and forth. Then almost everything else is carbon-based, and then if it's functionalized, means it has non-carbon and hydrogen atoms on there. All right, and then fuels, what that means is basically jet and gasoline for your car are mixtures of the things. They're not pure one compound, because you kind of saw here on the last slide, there's lots and lots of combinations, depending on how many carbons and how many bonds, and there's millions and millions of possibilities. It won't be on our exam, but just a little foreshadowing, which is good for people that have to take OChem. Towards the end of the semester, you should buy a modeling kit if you're a bio major and have to take OChem. If it's got a double bond in it, you'll see ENE. If it's got a triple bond, you'll see YNE. Aromatic, or the benzene ring, is that 6-membered ring that also has some double bonds. Again, not on our test. Here's just some classic examples. And all of these things have different uses, right? This is natural gas. If you've ever lived somewhere that had a gas stove, the one you fill up at the gas station or hardware to barbecue outdoors. This is what's in lighters, the liquid that you see, but when you push down, it's actually a gas. Gasoline is carbon 6, sometimes 5, but although its boiling point is pretty low, but usually it's more like carbon 6 to carbon 10. Then I think it's weird they put this in here, ripening agent in fruit, but this is what the gas that gets used to make all kinds of plastics and polymers and rubber. Then this is really high energy, which we'll see later on, and that's why they use it for welding. Okay, I don't think we need to go over the naming of all of it. The prefixes are the same that we already saw earlier in the semester, but I'm not going to test you on any organic chemistry. Functional groups, what that is just where it's no longer just carbon and hydrogen. And carbon and hydrogen bonds are pretty strong. So for the most part, what we do with hydrocarbons is burn them. And that's the ones we burn aren't very useful for other things. So to make them useful, you've got to put functional groups on there, right? It's in the word function. Again, not on our test. This is, again, the first week of OChem. So if you have to take OChem, this is, these will make more sense once we get to the last couple chapters. And this is, you have to have these memorized and know these like the back of your hand in OChem, but not for our class. And then here it just talks about how these are used and where you come across them and what they're good for. Okay, let me switch here. All right, so this is our last chapter before our first exam. So I think our first exam is in 2 weeks from today. So the goal is to finish this chapter, and it's a little bit long with newer and harder concepts, or just expanding really on the last half of the last chapter. So we've moved along kind of quickly, I know. I think the first 2 chapters are sort of general science reminders, and that's why I don't think they needed as much attention. And there wasn't that much math. And on these online tests, you kind of need to put more math so that it's less, looking at your notes and more what you know how to figure out. Okay. I'm going to grab a water. I'll be right back. Okay. So last chapter, it introduced chemical reactions and said balancing them and just called it that. There's a specific term for that. It's called stoichiometry. So whenever this is a word you should memorize and know, when you hear this term stoichiometry, it specifically means balancing the number of atoms in a chemical reaction. And the way you do that, which we covered and saw last time, is about manipulating those coefficients in front to get the same number of atoms, right? You can't change the subscripts behind. When you do that, that changes the molecule, right? So the only thing you can do is manipulate those coefficients in front. And then the ratio in which these are related is called stoichiometry. So you'll see it used not just saying balance the coefficients, but once they are balanced, it might say use the proper or use stoichiometry to determine. And so what it's introducing here is that once you have it balanced, then these are they're going to be used as conversion factors, right? There's 24 hours in a day. In the combustion of C18 is octane. So in the combustion of octane, it's in a 2 to 25 to 16 to 18 ratio. Just like there's 24 hours in one day, there's 2 octane molecules for every 16 CO2. And we're going to use those conversion factors. Right, so here's sort of the take home back to we're going to do more dimensional analysis, but now, in those first 2 chapters, any dimensional analysis we did was kind of stuff that was just general science, and now it's really specific chemistry. All right, so what does the stoichiometry do? It lets you predict things, whatever it is. So again, for example, if you were trying to figure out like your carbon footprint and your carbon output, so how much CO2 comes out of some process, and environmental engineers do this kind of thing, where they estimate the amount of, let's say an aircraft carrier. Most of those are nuclear, but I don't know, let's say a tugboat, if it's going to run, I don't know, 20 hours a day in a harbor, and how much gas it uses in one day times 365, and then all the burnt fuel gives off a certain amount of CO2, you can figure out its CO2 or carbon footprint. Right, then in the questions, right, whatever you were given, you wanted that same unit on the bottom for the dimensional analysis. So what this example is showing you is, if it asks you a question about how much CO2, and the initial amount it gave you was some value for CH18 or octane, then you need to set up the conversion factor like this: 2 on the bottom, 16 on the top. Right, units cancel. The dimensional analysis it's really critical. So it's good in those first chapters to go look at problems and like the worksheets, and make sure that you can do the simple ones, by writing them out and keeping track. That way, when we get to these other ones that are new, it doesn't seem so foreign. Okay, so let's do one. Estimate the mass of CO2 produced in 2004 by the combustion of, and this is some ridiculously huge number, times 10 to the 15. A gram of gasoline isn't very much. That's probably like, I don't know, 10 drops or something, or 3 drops. But 10 to the 15th, it is a lot. Okay, so they're basing this off the last slide, right? Really, gasoline is a mixture of different molecules, but generically here, we'll take this molecule octane, and that's where the number you see at the gas station has an octane rate. Okay, so they gave us gasoline, which we're going to assume is octane. So the units don't match up, right? The units in a chemical reaction are moles, right? These coefficients. They gave us grams. So we got to get out of grams and into moles. And then we use the values in the balanced equation to get from moles of thing they gave us or talked about to the moles they want to know about. And then this one wanted to know the mass. So our last step is to change out of moles and into grams. And this is really typical, where you're given an amount, you need to change to moles, use the mole-to-mole ratio, and then back to another amount. Whether it's a solid, liquid, or gas, whether they give you density or a volume, any combination of these, but these 3 conversion factors, and the first one and the last one will vary a bit depending on what the reactants are, solid, liquid, gas. But this middle coefficient is going to always be from the balanced reaction through the rest of the semester and the rest of the year. Okay, so you need to go grab the masses for these. And usually I just give you these on a test. Or there might be one example where I want you to add it up and find it yourself. But especially in an online test, you can just type in CO2 to Google, and it'll give you the value. So it's a little silly for an online test. But in the future, this may not be grams to moles. It could be like a volume. Then you would need the density or something, or a gas. Anyway, but regardless, you want to get into moles because that's how we relate the two, right? And this is from the balanced equation. And you can put this in lowest common denominator if you want, right? It doesn't need to be 16 to 2. You could reduce it to 8 to 1. It doesn't matter. All right, then last, back, out of the moles of the thing we're interested in to the mass. All right, so with these, does the number make sense? Well, we're dividing it by 100, then multiplying it by 8, and then multiplying it by 44. So I'd expect the number to be bigger, but not many of orders of magnitude. So from 10 to the, to the 15th to the 16th seems about reasonable. Right, and this is where that dimensional analysis is important. So you can cross out those units and know that you have the right units. All right, here's another one, and they're going to change up how we measure this. According to the following equation, how many millimeters of water, right? So here's where we're going to use a density or something, right? Because it's asking us about a volume, are made in the combustion of 9 grams of glucose. So this is you eat, I don't know, let's say you have a donut or something for breakfast. They have a lot more than this, I'm sure, but 9 grams of sugar goes into you breathe oxygen all day, you breathe out CO2, and then the combustion of carbon and hydrogen always give off CO2 and water, and so this water is being produced. So how do we get there? Well, the grams don't do us any good because the balanced reaction is mole to mole ratio. So we got to get out of grams and into moles, and then the moles are the two things we're interested in, and that was the sugar to the water, and it's in a 1:6 relationship. Okay, then once we know the moles, we can go to grams and then use density to get to the volume. And this isn't much of a conversion, right? Normal water, pure water, it's 1 gram per mil. So, here it is, more dimensional analysis. One little extra step with the density, right? Our grams cancel, we're into moles. Sorry. Then 1:6 from the balanced equation, then out of moles and into grams, and use density, which again isn't much of a conversion since the value is 1. But if it was some other liquid or say a gas, the density wouldn't be 1, and so there would be that extra conversion. The limiting reactant. So this is something that you inherently are familiar with, just not in chemical reactions, right? So when you go to the grocery store and you buy food to cook with, whatever it is you're cooking and whatever you're doing, they don't sell the food that you're buying in perfect proportions for whatever it is you're making, right? So, if you're making a smoothie, they don't usually sell you just one fruit or half. If you only need a half a banana, or you need more than one strawberry, that kind of thing. So whenever you have these chemical reactions, it's really difficult to measure out the amounts to exactly the right stoichiometry, 2:1, 6:1, 3:5, whatever it is. And a lot of times it's easier to make the reaction happen by adding an excess of something until it's consumed all of the thing that there's less of. And usually you do this, you put in the excess of the thing that's really cheap that you don't care as much about, right? Things that are cheap we don't usually care as much about. Okay, so the thing you run out of first is obviously the limiting, and since we're adding reactants together, the thing that runs out first is called the limiting reactant. Limiting reagent, this is used interchangeably. I would say when you're learning it, they call it more the limiting reactant. And then once you've taken it and studied it and know it, and you consider yourself to be a chemist, it's much more common to hear the term limiting reagent, but not super critical which term you use. Okay, so of the two, one has to be limiting. That means one must be in excess. Right? The one that's in excess and that there's more of is called the excess reactant. And a lot of times just the reactant is left off there. And usually, again, you don't care about the excess one. A lot of times this is like water, sugar, salt, or something. It's, it's not something that is critical. You talk about the limiting one because the excess one is still around. All right, the amount of the product that can be made from the limiting reactant is called theoretical, right? The one that you have excess in, you could make more and more of, but you run out of the other one that's important first. So there is a limit to the amount that you can make, and that limit comes from the one that there's less of, and that limited amount is called the theoretical yield. The other thing to this is that in a lot of chemical reactions, A and B, let's say, can go to form molecule C, but especially in the world of organic chemistry, sometimes A and B can combine in multiple ways, and they can form different new chemicals, not just A and B form C, but they can form D and E, etc. And a lot of times you don't want, molecule D or E, you only want C. And other times, molecules A and reactants A and B, they slow down and they won't make, they'll only make, 50 or 60% of molecule C, and you can't get them to continue to react. So you don't always get 100% even of the limiting reactant. So the amount that you do get is called the yield. And again, when they introduce it, they use actual, but after that, generically, they just say the yield. They don't say the actual yield. Okay, so then not only is it generally less, it almost is, but it can't be more. And the actual yield divided by the theoretical yield is called the percent yield. And you're used to this. This is basically what an exam is. You have a quiz in one of your classes, there's 10 problems. The theoretical yield is 10 out of 10, right? The actual yield is the score that you get. So let's say you get an 8. Well, 8 out of 10 is 0.8, and you multiply by 100, that's 80%. So chemical reactions do this same thing. Like all percents, it's the actual over the theoretical times 100. Okay, so let's go back to our familiar reaction of methane. This is that one we balance, right? There's 2 oxygens and 2 oxygen molecules, and there's 2 waters to help it balance out, right? So those coefficients in red there, the 2 and the 2. Again, whenever you see a chemical reaction that already has coefficients written in front, you should assume that that's balanced. I'm never going to put in incorrect numbers and have you correct them. But if you see no numbers written, the implied 1 to 1 to 1, you should double check. So it's kind of rare for chemical reactions to work out perfectly 1 to 1 to 1. Okay, so this is introducing doing the quick math behind the limiting reactant. And molecules versus moles, you can use those interchangeably, it doesn't matter which. So this one's saying 8 molecules of natural gas and then 10 of O2. What's the limiting reagent? Right, so how do you determine this? What you need to do is take each set and see how many product molecules you can get. And it doesn't matter which product you pick. So here they're picking CO2, but you could pick water if you wanted, doesn't matter. So from the methane to the CO2, it's a 1 in front of both. So if you have 8 methane molecules, it's in a 1 to 1. You could get 8 CO2 molecules. All right, if you have 10 oxygen gas molecules, how many CO2 can you get? Well, it's in a 2 to 1 ratio, right? So this is where the dimensional analysis is important. The 2 O2 on the bottom, those cancel, 1 of CO, and you see you get 5 molecules. So the O2 is the limiting reagent, limiting reactant. you can't make the 6th or the 7th or the 8th molecule because you no longer have the methane. You don't have the carbon. It's not possible. Right, so less CO2 and in this instance, but it wouldn't matter if you picked water. The math works out the same, right? Because they're all equal to each other by the correct ratios. The point is less CO2 is made, and so that's your limiting reactant or limiting reagent. All right, so this is going to do an example. There'll be one of these on the test. These are a little bit lengthier problems. So there'll be an easier limiting one, and then there'll be a full limiting one. I would save the limiting reagent problem, and you'll be able to spot it for maybe the last problem you do, because they're just a little bit lengthier and all the problems are worth the same. So let's look at this one. All right. We've got 28.6 kilograms of carbon are used to react with 88.2 kilograms of titanium oxide in the reaction below. 42.8 kilograms of titanium are obtained. Find the limiting reactant theoretical yield and percent yield. So this is actually true. The way they do this in factories is they take carbon is, coal basically, or charcoal. They take titanium oxide, which you see that in it's a white pigment in paints and sunscreens and things. But to get titanium, the metal, you got to get the oxygen off, which is a difficult thing to do because oxygen bonded to other things are usually strong bonds, and this takes a lot of heat. It's a furnace. Basically, they don't just mix the two, right? These are two solids, so they don't just mix these two like flour and sugar or something before you make cookies. They actually burn and use tremendous amounts of heat. And it's a blast furnace, and then you get a gas coming off. And this is a trick in the chemistry world where one of your products is a gas, then it leaves, and there's no way for the reaction to go back in the other direction. And it also doesn't get in the way or crowd the product. But this is how they make titanium metal. Okay, since there's two oxygens, just the balancing part I forgot to mention. Since there's two oxygens on the TiO2, the carbon is going on. They're saying it's making CO. When I initially read it, I was expecting CO2, but whatever, they want to do CO. So then they gave us these amounts. So how do we find out which one's limiting? We take our two reactants and do the dimensional analysis to predict, given these two, how much titanium would they produce if it was 100%. Right, so from the kilograms, really we want to be in grams, right? Because that's what's off the periodic table. Then the molar mass of each. And then we pick either product, doesn't matter, but let's pick the titanium since the mole ratio is 1. That makes it a little bit easier. And it's the one we care about. And which one is smallest of these two? All right, once we know which one is smallest, that'll then tell us the mass. If it went to 100%, we'll compare that to the amount they gave us. Change it to kilograms first. The units have to match. And then divide the two and we'll know the yield. All right, so the extra step that's in this one that I won't put on an exam is, from kilograms to grams. And they're doing this because this is more the scale in some, industrial reactor. All right, then the mass of all of our different species just off the periodic table. And then the ratios from the balanced equation, right, are 1:1 and 1:2. All right, carbon is what they picked first. Doesn't matter which one you pick first. Out of kilograms into grams, 12 grams per mole. Our balanced equation is 1 mole of carbon for every 2 moles of carbon, sorry, for every 1 mole of titanium, right? The 2 you see here, and then the 1. We work through that and we get 1.19 times 10 to the third, right? Because these are reported in kilograms, so we expect a bigger number. All right, so the important thing here is you can't just look at which number is bigger, because you have to do these corrections and dimensional analysis by the molar mass and the mole-to-mole ratio. 88.2, we changed to grams, mass of titanium oxide off the periodic table. It's in a 1-to-1, so that's not much of a change. And we get to the moles of titanium that it would produce. So notice here, right, the thing that was bigger value-wise produced less. So you can't just look at the two amounts and assume that the smaller one is the limiting reagent. Double check our units cancel, and right, the thing that we had more of, the titanium, is actually the limiting. It's, even though the mass was more, due to the molar mass and the molar-mole ratio, it's actually the thing you run out of first. So it's our limiting. Now that we know what's limiting, we can find out how much it, in theory, if things were perfect, would produce. So the molar mass of titanium gets us to what it would produce if it was 100%. Now, it's not 100% because the two numbers don't match. The theoretical is not what they gave us, right? The actual was 47.87. So divide that by our theoretical we found, multiply by 100, and about 80%. So the percent makes sense. It's less than 100, which is what's expected. But there's, other than that, there's, you'd have to be someone who works at the plant to know, what their normal percent is. So here's everything that it asked. And I think the one on the test I put is, which is the limiting and the percent. And it's a multiple choice, so you can at least guess, but it is a lengthier problem, than some of them. It's a few of the things we have looked at, like changing from Celsius to Fahrenheit. That's a bit of an easier problem than one of these. And this is just what I was saying, right? It's less than 100%, but you'd have to work at the plant or done this before to know what the average or usual yield is. All right, so what's typical in these slides is where it shows a problem like that and really goes slowly and shows you the animation step by step. So what's good to do is, go back if you get stuck or need to do these, is you can go back and hit the animation and try to work this out. And when you get stuck, you can hit the animation and it takes you one step further, and hopefully that gets you back on track. This one, it's going to give you a few less hints and go through it a little faster. Here, how many grams of nitrogen N2, that's nitrogen gas, can be made from 9.05 grams of ammonia reacting with 45.2 grams of copper oxide. So in this one, we've got 2 reactants, we've got 3 products. There's already coefficients in here, right? 2 to 3 to 1 to 3 to 3. So if there's already coefficients in front, it's already balanced, right? We don't need to worry about balancing it. Here's what they gave us. It's asking how many grams can be made, which indirectly is asking you which is the limiting reagent, because it gave us the gram, some values, grams in this case, amounts of both of the reactants, right? So if it gives you the amount of both reactants, that's indirectly saying which is the limiting reagent. All right, so how are we going to find out which one is the same thing. We need to figure out the theoretical yield based off both amounts of both reactants given, right? And then the smallest of those two will tell us which one to use. All right, so we need the molar masses of each, and then we've got the mole-to-mole ratios from the balanced equation. All right, they picked to do the ammonia first. It doesn't matter which. Ammonia out of grams into moles off the periodic table. Then from our balanced equation, 1 to 2, right? Our units cancel, and we see we get 2.66 moles of nitrogen gas. Okay. Doesn't do us any good till we have the other one. 45.2 grams of copper oxide, molar mass off from the periodic table, mole to mole ratio is at 1 to 3, and we see we get a smaller value. So again, even though the larger mass given in the problem, it's still the limiting reagent because the molar mass of the reagent given is larger than for the other reagent, ammonia, and then the mole to mole ratio, we divided it by a larger number, right? 3 to 1 versus 2 to 1 above. All right, so we know which one to use, and that's in theory, the amount of moles of N2 that could be made. So then last step here is use the mass off the periodic table, and that'll get us to the theoretical yield, which is what this indirectly is saying, how many grams of N2 can be made. This one didn't give us an actual yield to find the percent yield. It just wanted to know what the theoretical is. And it asked it in a roundabout way, right? It said how many grams can be made. Then does this make sense? Sure. You don't know until you do the math, but when it's here above, you can see we're dividing by a much bigger number. Ballpark 20 versus 80, and then 2 versus 3. So even though ballpark it was 10 grams to 45, we divided by 2 numbers that are much bigger than above, so it makes sense that the copper oxide was the limiting reagent. Okay, so most of that was grams to moles, and moles back to grams. The thing is that solids don't really mix together that well. So when you have cooked anything, if you've made cookies or a cake or whatever, solids don't really mix together too well, right? Think of every recipe, everything you've ever done in the kitchen. You usually need a cup of water or a cup of milk, an egg, something like that. Flour and sugar don't. I mean, those are kind of powdery, soft solids, and those things mix together a little bit better. But chunkier, stiff, hard solids, they don't mix together too well. So usually you need some liquid in there to let the things flow, and especially in a chemical reaction where the molecules need to find each other. All right, and we already talked about solutions, what they are. The solutes, the thing that there's less of, right? And change of state means, like when you throw salt into water, it looks clear and like it became water. And solvent, and for us, it's almost always just water. That's going to be the thing that stays the same, and it is the majority and allows the different solutes to move and find each other. All right, we covered mixtures a little bit, and mixtures obviously can vary in composition from one to another. This is not what you're used to when it comes to products, right? So this is a big thing for global restaurants where, or if you produce something, right? If you're drinking a Coca-Cola, whether you're in China or Africa or here in the States or wherever, they want it to taste the same. So it needs to have the same mixture. All right, if something's pure, then it has the same composition, right? And salt water does this, right? So the things like the Dead Sea and the Salton Sea, these places, and usually where that happens is you get salt, it accumulates, and these things are usually below sea level. So as water drains from different sources and takes ions with it and flows down to a place that's below sea level, then the salt continues to accumulate and they get saltier and saltier and higher concentration than the oceans. Right, so to know the solutions, you got to know how much of each one is in there. And we do this by what's called a concentration, right? And these terms are generic here of concentrated versus dilute. The value usually is 1 molar, but this is sort of like young and old, right? So life expectancy is ballpark 80 years. And so if you're 40, you're kind of in the middle. And if you're, younger than 40, you're sort of young. If you're older than 40, you're sort of old. But it's really relative to, for us as people, it's relative to your age, usually who you call young or old. Okay, and so this is what your laundry soap kind of looks like, right? It comes real thick when you buy it from the store. You pour just a cap full into the washing machine, then it fills up. And this is what it looks like, right, in the washing machine. So it comes really concentrated, but you don't need it at that level. And so we use it dilute to wash our clothes. All right, the concentration unit to describe this that we'll use all semester, all year, you'll use it in OChem, is called molarity. And what this is it's the amount in moles divided by the volume of the entire solution in liters. So mole per liter is molarity. This is just like density, right? Density was mass divided by volume. This one is molar amount divided by volume. So when you have lab where you work, there's workers in the stock rooms all across all these campuses. And when you're using some solution, they make it up to start the week. They make some huge batch of it. They have a piece of glassware like this where it has some marking on it, and they throw in weigh out on a scale, and then they toss the solid in. Then you add whatever liquid it is. For us, it's almost always water up to that mark. And then usually they put a cap on it and you invert it back and forth. Some things you just let them sit long enough and they mix. Some of them you have to invert. But regardless, you want the same concentration for everyone doing that same work. So you make one big batch and then pour it out and use it. And that works really well with water because water doesn't evaporate very fast. And if you keep a lid on things, it shouldn't evaporate really at all. Okay, so there'll be one of these on the test. You're going to need to do molarity all semester, all year long. This one, we're finding the molarity, 25.5 grams of KBr in 1.75 liters. So we need to go from the grams to the moles, and then they gave us the liters. This is really similar to a density one. It's just we're using the chemistry terms, moles and grams. All right, so first out of mass and into moles from the mass off the periodic table, and then molarity is by definition moles divided by liters. So we need to divide our moles that we just found by the liters. So grab it off the periodic table of mass, divide the mass given by the mass of the periodic table. That gets us out of grams into moles. the little underscore here is just reminding you of sig figs. You'll see on our exams, I'm not stickling you on sig figs. And you can see up here, right? The number given has 3 sig figs, both of them. So you just keep all the numbers on your screen of your calculator. You do the math, and then you just round to 3 sig figs. All right, so we take the moles, we divide it by the liter amount they gave us, 1.22. Does this make sense? Well, you wouldn't know this, the little check, until now, but 1 molar is sort of the normal amount, and it's really hard to measure out tiny, really, really small amounts. So 1 mole, 0.1 to 1 molar are sort of the normal ones, and then 18 is extremely high. Most liquids can't handle large amounts of solute. 18 molars, very much on the high side. Usually 10 is kind of extreme. This 18 is only for certain things that really like water. There's just not, most solids can't mix, to 50%, right? Once it's over 50%, then the solute and solvent technicality would change, would flip-flop. Okay, so why do we care is that, again, it's really hard to mix 2 solids. So almost everything comes as a liquid. You mix them as a liquid, which means we're going to do the same thing. And especially those that have lab, you'll do the same thing where you're doing the percent yield and the limiting reagent, but it's based off the molarities, not the grams. All right, so let's say sugar has a concentration of 2 molar. All right, if there's 1 liter, then there's 2 moles. If there's 2 liters, there's 4 moles, right? This is another conversion factor that we're going to use. And you can flip-flop it and arrange it either way. So conversion factor, just like 24 hours in a day, depends on what we're being given and what you're being asked, how you manipulate the conversion factor. All right, so let's do one of these. How many liters of 0.125 molar sodium hydroxide contains 0.22 moles of sodium hydroxide? All right, there's what they gave us. We're looking for a volume. We're going to go from the moles they gave us and get to that volume by the molarity. So again, it's more dimensional analysis, right? They gave us moles, so we want to flip that molarity and have the moles on the bottom, the volume liters on the top, because we want to carry through and we want the liters as an answer. Then does this make sense? The concentration was about half of what they gave us. So then the volume should be, roughly 2. Right? You can see these numbers are about double or half of one another. So okay, dilution, which we already saw. And if you use liquid laundry soap, then you do this every time you do a load of wash. In chemistry stockrooms, this is how they ship them, and this is how they ship that soap, laundry soap. It comes as a concentrated stock solution, and then we make solutions of lower concentrations from the stock ones. You add more solvent, right? You pour just a cap or a splash of the liquid soap in, then you hit the button on the wash and the whole washing machine fills up for, it takes it a few minutes. And so there's less soap in there per volume. All right, so how do you calculate and know the math of these two? Well, it's this simple equation, and inverse proportional, what that means is since you're multiplying them by each other, if one goes up, the other must go down. And this equation is worth, write down on your periodic table or on the wall wherever you take the exam, there'll be one or two of these on the test. This is a common thing you have to do. So you could set it up and do it in our typical dimensional analysis way, right? Volume of A to moles of A, moles of A to moles of B, and then volume of B. But our M1V1, M2V2 does that for us. So this looks just like our grams to moles, except most of our solutions, it's easier to measure out volumes, right? If you have a liquid and it's more difficult to measure it out because then you have to do it on a scale, whereas you can just pour it into a container. All right, so let's do one of these. Watt volume, that tells us what we're looking for. 0.15 molar KCl is required to completely react with 0.15 liters of 0.175 molar lead nitrate. Then it gives us the reaction of how they're reacting. Okay, so there's already a coefficients in here, these twos, so we know that it's balanced. What did it give us? It gave us information on the KCl, and it gave us information on the lead. All right, so they're in a 2-to-1 relationship. It only gave us the molarity, it didn't give us the volume. So what we need to do is find the molarity. We want to find the volume of the KCl, so we need to find the molarity of the lead. Go from the amount of lead given to the molarity of the lead. We know that it's in a 2-to-1 ratio here. And then we know the molarity of the KCl, and that'll get us to the volume that we need. So basically what it's telling you is that the KCl is, if you don't pour enough in, then the lead will be the limiting reagent, but it doesn't want to have a limiting reagent. It wants it to be ideally 1-to-1. So measure out enough KCl so that the lead isn't limiting and they're as close to 1-to-1 as possible. So let's find out how much lead's there, right? They said this is the volume they used. This is the concentration of that volume. So the lead cancel. Right now we're in moles. The KCl to the lead is in a 1-to-1 relationship, and then this is how much KCl was used. So 0.35. Does this make sense? The concentrations were pretty close, and then it's in a 2-to-1 relationship, so you should need to, more. And this is, close to that 2-to-1 relationship, a little bit more. So it makes sense. All right, so this is just going to take a quick look on what happens to your solute when you put it in. Now, keep in mind, chemistry is like a Venn diagram. We haven't talked about the attractive forces. You can't know what those are until you do the chapters on bonding and look at things how they're together. But you've held, a piece of bread or a sugar cube, right? And it's held together. It doesn't fall apart like a liquid. So there's certainly interactions there. But if you throw a sugar cube into water, it slowly dissolves. So here's the sugar cube, the purple spheres. They're interacting with each other and holding each other together. But then the water molecules come in and interact with them. So the sugar molecules have to break apart their interactions together, and then you get the water molecule interactions. So the same thing, whether it's salt or whether it's water. And so these different forces are at play, and that's what makes and determines whether something will dissolve, right? So salt and sugar classically do dissolve, but a lot of things don't mix together, For example, when you've been in a harbor and you see oil and gasoline floating on the surface of the water, they don't mix evenly. They don't make a nice solution. And then things have limits too. If you like sugar in your coffee, you dump a couple spoonfuls in. When you've put in too much, it starts to fall out and sit at the bottom. And when you're done with your sugar, people who like a lot, you'll see a sludge of wet sugar at the bottom. Right. So, a big part of chemistry is getting to see what you've seen with your eye and understand it on the atomic level. And that's what this is showing here. So this is showing a chunk of salt, and a sugar cube's a little bit like more probably what you're used to. Most people don't put salt in their water that they drink. But what you can see here is that when you throw the chunk of salt or sugar in there, the water molecules come to the surface of it. They pick off the molecules and interact with them that are on the surface, and it dissolves just like an ice cube melts, right? The interior molecules are protected, and the outer layer, just like an ice cube, is what melts away. All right, this is just a little foreshadowing. We'll see the term a little bit, and things are called electrolytes or non-electrolytes. And the reason for this is this type of setup, right? If they have ions, then there's a charged nature to them. And in this little setup that you see here, right, table salt is sodium chloride. When you pour sodium in here and you have the battery, in order to complete the circuit, the positive ions move towards the negative electrode and the negative ions move towards the positive electrode. Sugar, like most hydrocarbons, has no ion, no charge to it. And so it doesn't matter how much sugar you pour in here. You'll never complete the circuit and see any electricity. So things that do have charge to them are called electrolytes, which basically is the ionic compounds. And things that don't are called non-electrolytes, which are your hydrocarbons and organic things for the most part. So there won't be a test, question on this. This is just some vocabulary. And it'll be more important in Chem 162, but you'll occasionally see it, and this is a good chapter to introduce it. Again, to conduct electricity, you have to have charge and ions that can flow, and that's ionic compounds. As they break apart, right, table salt is sodium chloride, and the sodium and the chloride ions break apart, and then they can flow. Non-metals and covalent molecules and things like sugar are a single compound. There's no ion nature to it. So even though they'll dissolve in water, there's no charge. We'll see that acids are the exception to this, but again, this is foreshadowing for future chapters. So here's just showing on the atomic level, right? So table salts, these two separate elements, they're charged, they break apart, and the separate ions can float around and they can move in solution. Sugar molecules have no charge. So when you throw a sugar cube in water, yes, it breaks apart, but it's just individual molecules floating. There's no charge associated with it. All right, acids, the last chapter we looked at introduced the names. Now we're going to just introduce how they react a little bit. Right? All of our acids had started with an H in the formula, and then they generally had either a polyatomic ion or a single element that in the periodic table is over near 6 or 7, group 6 or 7. And so these are the exceptions, where ionic compounds are a metal and a non-metal. Acids are the one non-metal exception that can have some charge to them. So whether something is strong or weak just depends on if the reaction goes 100% or if it stops somewhere in between. And there's math associated with how far to completion these reactions go. So the double arrow here is meant to say and show you that it doesn't 100% go in the forward direction. And we'll do all this math in Chem 162. So again, this is just introducing the verbiage, and because you'll see it in reactions and it wants you to know a little bit about it, but we won't do this math associated with how far it goes. You know, is it 50%? Is it 5%? The strong ones are 100%. You can't measure any of the reactant left over. And usually you do this usually in Chem 162, where you'll have this setup. It's usually done with a voltmeter, not an actual light bulb, but you can measure the voltage, and you'll see that some things dissociate completely and you can get a higher voltage, and other things, you know, the light bulb is either dim or barely on because there's no ionic nature to it. And again, that depends on how far these reactions go. You know, if it goes 100%, then the ions can flow. And if it only goes 1 or 5%, and you can't, there's a limit to the concentration you can have, then you're going to have a dim light, or a voltmeter will barely have any voltage reading on it. Kind of like if you've ever licked a 9-volt battery. If you lick one that's dead, you know, there's not much charge to it, where if you a brand new one. Again, more foreshadowing here. These ionic compounds, some of them dissolve just like table salt. They do it very well, and others of them don't like to be in water, and they never dissolve. They just sit at the bottom. These terms are called soluble. So when a solute, whatever it is, likes the liquid that it's in, it's called soluble. If it doesn't, it's called insoluble. This again these are generic terms. Sort of 1 molar and above are soluble, and below the 1 molar, below 0.1 is insoluble. Again, relative terms, just like young and old, right? It depends. You know, if to most of us 5 years old is young, but you know, if you're 2 years old, then 5 years old seems older. So these things are relative. And again, it's just introducing this. You'll do the math behind these in 162. It's just these are chemical reactions, and they want you to have a little bit of exposure to the vocabulary of it. All right, let me check. We're almost out of time. We're basically out of time, so this looks like a good spot to stop. So as usual, we'll stop here. I'm undoing the muting stuff. So you know, when it's over, the recording, I'll post it on La Lima. I always hang out for a while afterwards if anybody wants to ask any questions or talk about anything or clear it up. I think we've made pretty good progress as I look at this. You know, we're like halfway through the chapter, which means we could probably finish that next Monday, and that would give us next Wednesday and the Monday after to do nothing but review, which I was expecting to get to 1 day of review, but 2 would actually be better. So, okay, I hit the unmute, so if you want to ask any questions, unmute or chat box, and if not, I'll have a good weekend and I'll see you Monday.
Yeah, so I have a question. So what makes certain acids dissociate more than others? Like, why is HF weaker than HCl?
It has to do with stuff we haven't covered yet. There's something called electronegativity, and it's the element's preference to hold on to the electrons. It has to do with the length of the bond, so the size of the atoms, right? As you move down in the periodic table, the electrons moving around the nucleus kind of look like the planets around the sun. And the electrons go in to make the bond, and the longer the bond is, the weaker the bond is. So there's some little idiosyncrasies and trends. So sometimes you can look at it and predict it, but sometimes things go against the trend. So and sometimes things just are the way they are. Like, you know, if they go against the trend, you couldn't have predicted their behavior.
Okay. And then you said all acids are aqueous, but what about like glacial acetic acid and like concentrated sulfuric or something?
They're still aqueous. There's still water there. They're just really concentrated. It's like the soap. So like HCl especially, it is a gas. So when you take the lid off concentrated HCl, it'll actually steam like water that's boiling on a stove. But things that don't have boiling points that are high, um, they can, something that's a gas, you can put it in there, and that's why like HCl where it's escaping. But other things, even if they are very concentrated, you don't see it steaming or something. They love water. Like, it's really hard to have them dry. So we basically just don't bother trying to make it happen. I can't think of like, another substance that a common person has exposure to that is always like sticky and wet. Like, it just doesn't come. They just love water so much. So when you make them, it's real. Like, removing water is very difficult. If you're, like if you take a lighter and you put it to a glass cup, you'll see there's moisture on there that you can't see with your eye, and you'll see the moisture on it heat up and leave the piece of glass. If you've ever been in the desert, you rub your feet together and you can make static electricity. That doesn't happen when you're in a humid tropical environment. You can see water beat up on, like, have you ever been somewhere that's really hot and tropical and you're in the air conditioning, like your sunglasses, this is common. You walk outside someplace that's cold and then your glasses fog up immediately. So even though you don't see it, like, water moisture is everywhere. And certain compounds just love water and interact with it. So
Yeah, thank you for that. And then my last question is, what's the difference between a gas dissolving in a liquid and a solid dissolving in a liquid?
Yeah, it's a good question. We cover the math behind it in Chem 162. So a gas, it has to like the water, and the solubility, the amount of gas that can go into a liquid is always much less because it's a gas, right? You've been underwater, you blow a bubble, it doesn't stay, it goes shooting up to the surface, right? So fish and other animals that breathe oxygen, they're alive, but there's a limit to it. So, like, that a gas expands. That's how a hot air balloon works. Hot air rises and stuff. And so one of the areas or places you'll see this is when a river in like Africa or something, somewhere wild that has a wet and dry season, the river overflows its banks. Some of the fish overflow, and then as it dries up and goes to the dry season, you'll get these ponds where things are still alive and fish are still in there. As the water evaporates and the pond gets narrower and narrower and shallower, right? As it gets sunny and hot, and when water is shallower, right, it stays warmer. The warmer the water is, the more the gas expands and leaves the liquid, and the fish start to die because there's not enough oxygen in the water for them to breathe and stay alive. And this is where, animals that want to eat the fish, it's easy. They don't have to chase them, right? They're just dying, and so they can go over there and eat them. A solid isn't going to expand like a gas out of the solution, whereas a gas can expand out. And that's the reason, soda bottles, you buy the ones with the lids on them. If you open a can, you basically have to drink it because the gas is going to continue to come bubbling out, and it's flat and in, whatever amount of time.
Yeah, okay, that clears things up. Thank you.
Yeah, cool.
All right, yeah, see you next week.
Yeah, see you Monday.
Yeah, see you Monday. Bye-bye.
Bye.